Remember, I've been reviewing basic affine algebraic geometry, so I already talked about quite a lot of those basic notions. I gave you the definition of affine variety. We talked about the coordinate algebra. That's part of the data of an affine variety. And the Zariski topology. And using that, I also talked about the notion of an irreducible variety. Those are the ones whose coordinate algebra is actually an integral domain. And then we talked a little bit about morphisms and comorphisms. Maybe I talked about the Null-Schlellensatz, which really boils down to checking it for affine n space. Okay, so that's where we've got to. So the first thing to do today is I want a few constructions. So that's kind of normal whenever you're seeing some new mathematical structure. You always want to be able to build lots of examples, starting from some very basic ones. And the basic ones that we have are these affine n spaces. So given them and the following constructions, we can then construct lots of nice examples. Okay, so we want to be able to construct new affine varieties out of old ones. So let me see, I'm going to give you 3 constructions. So the first one is probably one that you're familiar with, possibly if you've seen any of this stuff before. If Y is a closed subset of an affine variety X, well then you can make Y into an affine variety. So all you have to do, it's already given as a set, you have to say what are the good functions, what's its coordinate algebra. And all you have to do is you have to define the coordinate algebra of Y to be, so this is the definition of the functions. Remember, affine variety is a pair, a set, and then a collection of functions on that set. So the collection of functions, well, they're the functions for all f in the coordinate algebra of x. So the given good functions on x, and they're just the functions on y that you obtain by restricting. So the point here is that restriction defines a actually surjective algebra homomorphism. From the coordinate algebra of x to the coordinate algebra of y. And so that's the surjectivity is just immediate from my definition. I'm defining the coordinate algebra of y to be the set of restrictions of functions in the coordinate algebra of x. So that restriction homomorphism then, it maps k of x onto k of y, and that means that the coordinate algebra of y will be the quotient of the coordinate algebra of x by that homomorphism, and the kernel of that homomorphism is just exactly the ideal of all functions vanishing on y. So that means the coordinate algebra of y is isomorphic to the coordinate algebra of x, quotiented out by that ideal of the functions that vanish on y. So great. So it's easy just using the correspondence theorem to check that does indeed make y into an affine variety in its own right. You have to check that axiom, right? That the points of the set y correspond to the maximal ideals of its coordinate algebra. And that just follows from the correspondence theorem. So then after having made that definition, then the inclusion of y as a subset of x is actually a morphism of varieties with phi star, the comorphism, being that restriction homomorphism that we just discussed. So such an inclusion, this phi, of a closed subvariety y into an affine variety x is called a closed embedding, for obvious reasons. So the data of a closed embedding is just exactly the same as the data of that comorphism, and that comorphism is a surjective algebra homomorphism. Okay, so closed embeddings, they're exactly just the same. If you just think in terms of the coordinate algebras and the comorphisms, the closed embeddings are exactly the surjective algebra homomorphisms. And I guess there's one kind of really most basic example we should write down. If you have any affine variety k of x, and you make a choice of generators, let's see, f1 up to fn, say, for that coordinate algebra, well, that choice is just the same. I think we talked about this already. That choice of generators is exactly the same as the data of a surjective homomorphism from the polynomial algebra in n indeterminates to k of x. This would be sending what, ti to fi. And so once you've got a surjective homomorphism from this polynomial algebra, which is the coordinate algebra of affine n space, to the coordinate algebra of x, well, that's just exactly the same thing as the data of a closed embedding of x into affine n space. Okay, so these are just the same kind of set of choices. Choosing an embedding of x into affine n space, a closed embedding, it's just exactly the same as choosing a system of n generators for the coordinate algebra of x. And so this is very important because this choice, it gives a choice of coordinates for x coming from the coordinates, so coordinates for the points of x coming from just the natural coordinates in affine n space. I guess then you could say you could think more about morphisms. If you have a morphism of affine varieties, as we defined last time, and if you picked coordinates for x, so you picked a closed embedding of x into affine n space, and you picked coordinates for y, so you picked a closed embedding of y into some other affine space, maybe affine m space, well, then in coordinates, if you have some point x, then, so having picked this closed embedding, x becomes an n-tuple sitting inside affine n space. The morphism phi sends x to a point in y, but that sits inside affine m space, so that's got coordinates. So we've got the first coordinate of phi of x all the way up to the mth coordinates of phi of x. And the point is that in this way of writing down the morphism phi, the function phi in all these coordinates that we've chosen, the definition of being a morphism, it's exactly equivalent to each phi I, each of these coordinate functions here being a polynomial. in the coordinates x1 up to xn of x. So that makes it rather easy to recognize morphisms. The basic moral of this is that a morphism is a polynomial function when you express it in coordinates. Doesn't matter what choice of coordinates you make, any choice, morphism will be just a polynomial function having made that choice. So morphisms are easy. That's the point of affine varieties. Morphisms are just functions which are kind of polynomial in nature. Okay, so that was the first construction, the construction of new subvarieties out of old, new affine varieties out of old by just passing to closed subsets. Second construction, so let's suppose you've got two affine varieties x and y, then x cross y, the Cartesian product of the sets. Well, that's a new set. We want to make it into an affine variety. So again, what you have to do is you have to say what's the coordinate algebra. And so the definition of the coordinate algebra of x cross y, a Cartesian product of the sets, is just defined to be the coordinate of algebra of x tensored over k with the coordinate algebra of y. So that's just the usual tensor product of two k algebras. That tensor product is a new k algebra. So its elements are sums of pure tensors, and a pure tensor, f tensor g, so f is a function on x and g is a function on y. F tensor g is meant to be a function on x cross y, so you have to understand what scalar it takes a point x comma y in the Cartesian product to, and you just calculate f of x, that's a scalar, g of y, that's a scalar, and then you multiply those scalars together in the field. So that's the coordinate algebra. Again, you've got to check the axiom, but all I'm going to write down about that is that the maximal ideal of this algebra, the kernel of evaluation at the point x comma y in the Cartesian product, is just the maximal ideal of x in k of x tensored k of y plus k of x tensored with the maximal ideal of y in y. So let me just finish writing that. There we go. And from that, I think there's really enough for you to be able to work out that axiom to check that indeed this does make x cross y into an affine variety. In fact, and this shouldn't be a big surprise, tensor product of algebras is that's the coproduct in the category of commutative k algebras, and the category of affine varieties it's really just the dual category, and so in fact this definition that I've just given, this gives the product definition in the category of affine varieties. In the general sense. So actually with this construction too, I didn't really need to tell you about affine n-space. According to this construction, affine n-space is just the Cartesian product of n copies of affine 1 space, because the polynomial algebra in n variables is a tensor product of n different polynomial algebras, each in one variable. Okay, so with this construction of product, you can get affine n-space out of the affine line. Okay, everything I needed to say about construction 2. Move on to construction 3. So the final construction, we've talked about closed subsets. I want to say something about open subsets. So again, let X be affine, and let's pick a function in the coordinate algebra of X. So remember we talked about d of f. So that was the set of points satisfying the equation f of x was non-zero. I called that the principal open subset of the variety x defined by the function f. So in fact, this d of f is itself an affine variety with the coordinate algebra. Remember, that's the only thing I need to tell you. You've got it as a set. I need to tell you what are the good functions. The coordinate algebra of d of f, making it into an affine variety, is defined to be the coordinate algebra of x localized at f. So this denotes the localization at the multiplicative set. That's just all the powers of f, 1f, f squared, and so on. So elements of this localization, they look like functions g in the coordinate algebra of x divided by some power of f. So this is for g in the coordinate algebra of x and n greater or equal to 0. Okay, so they look like fractions with powers of f on the denominator. And it's quite obvious that any such function g over f to the n, if you plug in some point in d of f, so that's a point where f of x is not 0, this makes sense because g of x is something in the field and f of x is something non-zero in the field, so you can divide by it, and so you could divide by the nth power. Okay, so g over f to the n, it's naturally a function on this principal open subset. Okay, so I've given you a set and I've given you the functions, but you actually have to prove the axiom. And well, one nice trick to do that is just to give a slightly different construction of the same affine variety. So let me see. I'm going to look at, so just to explain this little trick, what you do is you look inside actually x Cartesian product the affine line. So the coordinate algebra of this is the coordinate algebra of x tensored the coordinate algebra of the affine line, which is just polynomials in one variable. I think it's best to think of that as taking the coordinate algebra of x and adjoining an indeterminate t. So it's kind of polynomials in t with coefficients in the coordinate algebra of x. So what I'm going to do is I'm going to consider the closed subset, the vanishing set of the polynomial ft minus 1 sitting inside x Cartesian product the affine line. Right, so I've written just ft. I'm thinking in this formulation, this would be the polynomial f, the given element of k of x tensored with t in this formulation of the coordinate algebra. Okay, so ft, that's a function on x across the affine line, minus 1, that's just the constant function taking every point to the number 1. So this is a closed subset. It's an affine variety by the first construction that I showed you, its coordinate algebra. Well, it's the coordinate algebra of x across the affine line quotiented out by the ideal ft minus 1. It's easy to see that that's a radical ideal. And then really all you have to do to see that my localization that I told you was the principal open subset of D of f does the right job, is to see that this quotient algebra, k of xt, quotiented out by this ideal ft minus 1, is actually isomorphic to the localization. And this isomorphism takes, let me see which way round shall I go, it takes g over f to the n, it takes it to gt to the n, well, I guess the canonical image of that in the quotient. So, I mean, the idea here is kind of easy enough to get the hang of. In this quotient algebra, ft equals 1, I guess I should put bars over here. So it's sort of like t bar, the image of t in this quotient algebra is kind of like 1 over the image of f. And so t is like f inverse. And that's what I've done there, right? So I've sent g over f to the n, I've sent g to g, but this 1 over f has gone to t. So that's that map. So this then is the comorphism of a map from D of f to this vanishing set of ft minus 1, taking point x in D of f to the point x 1 over f of x. And so that's just a bijection between those two sets, the comorphism of that exactly corresponds to this algebra isomorphism. So since the comorphism is an isomorphism, this is just an isomorphism of affine varieties, and at the same time this is proving that my definition of D of f, with the coordinate algebra being the localization, satisfies our axiom of affine variety. Okay, great. So that's my 3 constructions: closed subsets, Cartesian product, and principal open subsets. We've explained how to make all of those into affine varieties in their own right. The last one is probably the most interesting one. It works perfectly for principal open subsets, but in general, if you want to make more general open subsets of an affine variety into an affine variety, well, you're not going to succeed. You actually need to go to this more general notion of non-affine variety to be able to make sense of a general open subset being a variety. So we're only ever going to talk about principal opens, and so that's important to stay within this category of affine varieties. Okay, so I feel like I'm going through quite a lot of different facts from affine algebraic geometry. There's just a couple more things I want to say, then everything will be in place. So I want to talk really quickly about dimension. So for this, let's suppose that x is an irreducible affine variety. Remember, irreducible means that the coordinate algebra is an integral domain. If you find yourself trying to talk about dimension when x is not irreducible, you're probably doing something wrong. Irreducible is crucial. You see, once this coordinate algebra is an integral domain, you can talk about its field of fractions. So this is called the function field. So that's the field of fractions of that integral domain. Okay, so you always have this function field for an irreducible affine variety. And then you define the dimension of x very simply to be the transcendence degree of its function field over the ground field k. So this is measuring the number of elements in a transcendence base for that field extension. So it's kind of the maximal number of algebraically independent elements of that function field over the ground field. For example, the dimension of affine n space is, of course, n, because the transcendence degree of the field of rational functions in n indeterminates over k, well, those t's are a maximal set of algebraically independent elements, and so that transcendence degree is n. Maybe one more example. If you have a non-zero f in your x, well then the principal open subset is irreducible, assuming x is irreducible, and its dimension, well, it's just the same as the dimension of x itself, as, well, the coordinate algebra of d of f is the coordinate algebra of x localized at f. So the field of fractions, well, the coordinate algebra is just a sort of a partial localization of the coordinate algebra of x. So its field of fractions is just the same as the full localization at all non-zero functions. So they have the same function fields, hence this transcendence degree is the same, and they've got the same dimension. I'm just going to write down a theorem, which I am not going to attempt to prove. It actually is a little bit harder than everything else I've said so far, but the theorem gives a nice characterization of the dimension of x. I've given this dimension in terms of the function field by this notion of transcendence degree, but there's a alternative definition in terms of the Zariski topology. So it's the maximum of all the natural numbers n such that you can find a chain x equals x1, strictly containing x2, strictly containing xn, which is not empty, where all the xi's are irreducible closed subsets. So it's this sort of maximal length of a chain of irreducible closed subsets. I guess the point is that each time you step down one, if you go from x1 to x2, you're going from an irreducible affine down to a proper irreducible closed subset. Those steps from x1 to kind of a maximal proper x2, that'll be a codimension 1 step. So you're making kind of n codimension 1 steps. This xn at the end will be one dimensional. Okay, so I guess each xi plus 1 will be an irreducible component of a hypersurface in the next one. So kind of codimension 1 each all the way down that chain. Okay, I think that's everything I want to say about affine algebraic geometry. It took me quite a long time to go through that, but that language is really fundamental. I want to put it into a nice setting, and I think by thinking about this concrete setting, you can really get familiar with that basic language of affine algebraic geometry rather well. So the setting that we're going to be talking about is the setting of algebraic groups. So it's taken a while, but this has of course been where we've been heading. Why I've been talking about affine varieties is I want to give you the definition of an algebraic group. An algebraic group is an affine variety G with the structure of a group as well. So affine variety plus group structure, so that the group multiplication so I'm going to always use the letter M for that. So that's just multiplication from G cross G to G, taking pair GH to their product under that group structure. And the inversion, I'm going to write I for that, so that just goes from G to G, taking an element to its inverse. I want these to both be morphisms of varieties. Okay, so that's just the total definition. It's a totally perfect, clean definition. An algebraic group, it's an affine variety and a group, so that the two group operations are morphisms with respect to the variety structure. Okay, so in particular multiplication, look, here we are. I've got G cross G here. That's that Cartesian product of these two affine varieties. That's an affine variety in its own right. So that was why we needed products in order to make that definition. Okay, that's the definition of an algebraic group. I guess at the same time, how about we define a morphism of algebraic groups? Probably obvious to you what that should be. A morphism of algebraic groups is a morphism of varieties phi from G to H that is also a group homomorphism. Okay, so we're just, everything we're doing, we're being consistent with the two different structures, the group structure and the variety structure. Let's just have just one little example right away, and that's the most important example, the general linear group GLN of K, which you know is n by n invertible matrices with entries in our field. So let's see why that's an algebraic group. Well, you have to think about all n by n matrices. That's an affine variety. It's just a copy of affine n squared space. I mean, an n by n matrix, there's n squared entries in that matrix. It's just the same as an n squared tuple of elements of the field. So this is affine. The coordinate algebra, for example, of n by n matrices, it's just polynomials in n squared indeterminates. So that's how I usually write it, as Tij. So Tij for I and j between 1 and n is just the ij coordinate function picking out the ij entry of an n by n matrix. So that polynomial ring generated by those n squared indeterminates, that's the coordinate algebra of the affine variety of n by n matrices. And then GLN of K, well, that's just the principal open subset of the variety of n by n matrices defined by the non-vanishing of determinants, just matrices with non-zero determinant. So that makes this set GLN of K into an affine variety in its own right, because it's a principal open subset of the affine variety, the full affine space Mn of K. So what am I doing here? I guess I'm using determinant. So I need to explain why determinant is an element of this coordinate algebra, why it's a polynomial function. Well, what I mean by det, of course, is I mean the determinant of the n by n matrix whose ij entry is this ij coordinate function. Right? So that's an n by n matrix with entries in this commutative algebra, this polynomial algebra. So it makes sense to take determinant of it. That determinant gives us a polynomial. It'll be a homogeneous polynomial of degree n by the usual expansion of determinant. And that's exactly the function where when you evaluate on any n by n matrix, gives you the scalar that's the determinant of that matrix. So, okay, great. So that's GLN of K as an affine variety. Its coordinate algebra will be the coordinate algebra of n by n matrices, so polynomials in those Tij's, and then we'll localize at determinant, so we also adjoin an inverse of determinant. It's also a group, and the multiplication is obviously a morphism. In fact, it's given by a quadratic, a homogeneous quadratic in the matrix entries. So the multiplication of matrices, which is the group operation on the group GLN of K, that's a morphism of varieties because the product of two matrices, the entries of that product, is given by a homogeneous quadratic in the original entries of the two matrices you multiplied together. And a little bit harder to see, but the inversion map is also a polynomial function if you think about the formula for the inverse of a matrix, where you do the ji cofactor and then you divide by determinant, those cofactors, they're n minus 1 by n minus 1 determinants, so they're polynomials in the matrix entries. And dividing by determinant is allowed because we've localized 1 over determinant. It is a regular function on GLN. Okay, so that's the algebraic group GLN. So I'm going to have a little bit of a digression now before I think too hard about the structure of algebraic groups. So if you've got an algebraic group, what have you got? You've got multiplication. You've got this inversion map from G to G. And I haven't mentioned it, but there's also this inclusion of the identity into the group. And thinking about the group axioms, one of the axioms is there exists an identity element. So corresponding to that, there's this morphism of varieties, the inclusion of this point that's the identity. So being an algebraic group, it's an affine variety, so it's got a coordinate algebra. And you can look at the comorphism of multiplication. Since that's a morphism of varieties, the comorphism will send the coordinate algebra of G into the coordinate algebra of G cross G, which is the tensor product, by definition of product of affine varieties. The inverse map, its comorphism, will give us a comorphism going from K of G to K of G, and the comorphism of inclusion, I think I usually call that evaluation. That's evaluation at E, which goes from K of G to the coordinate algebra of a point that's just the field, right? So that's just sending F to evaluation at the identity element. So all three of these are algebra homomorphisms. And you can take the group axioms and translate in terms of these comorphisms. So we'll get a structure on this coordinate algebra which is somehow co-dual to the group axioms. So let's do that. Let me start off with the easiest one is the associativity axiom. So the associativity of the group multiplication, that corresponds to an axiom about this M star. M star is usually called co-multiplication. I star is usually called the co-unit. So anyway, the associative axiom, the associativity of M turns into co-associativity of this co-multiplication, and I'm just going to quickly write that. I'm going to draw it as a diagram, but it's easy to see that this is what's going on. So the co-associative axiom, which is equivalent to the associativity of that group multiplication, gives you the following diagram. Where the maps here, this is M star and this is M star, and then this is M star tensored the identity, and this is the identity tensored M star. So this diagram commutes. Okay, so that's the first property of this co-multiplication. It's co-associative in this sense. Let's think about the why did I write co-unit there? Let me fix that. Sorry, that was not I star. The co-unit is this evaluation at E homomorphism here. So this is called the co-unit. So this algebra homomorphism from K of G to the field, that's what's called the co-unit, because it's the comorphism of the unit map for the group, the inclusion of the identity element. So let's see what does that look like. So let's see, I want to think about the unit axiom. What's the unit axiom? That's this axiom. So I want to translate the unit axiom of the group into some axiom involving this co-unit. So to do that, basically what you have to do is you have to write this unit axiom as a diagram. Let me see, I think I can so if I take G cross G to G, that's multiplication, and I can look at the identity cross G. So if I use inclusion of E cross the identity, that gives me a map from E cross G to G cross G as sets, and down here I've got this kind of obvious projection map. Which way around shall I write it? I guess I'll just write it this way. Just sending E comma G just down to G, right? So this is just projection onto the second coordinate. So that axiom right there, is that the right way around? Yes, EG equals G is just exactly saying that that diagram commutes. And from that diagram, now if I just dualize everything, I take comorphisms everywhere, I get, what do I get? I get K of G, tensored K of G, I get M star, K of G, and the coordinate algebra of a point is just the field, tensored K of G, and so this right here, this will be the comorphism of the inclusion of E, which is this evaluation at E. Right, so this is this co-unit right here. So we're doing if we're starting this tensor product, and we're doing the co-unit on the first tensor factor. And the comorphism of pra, well, that's just this kind of canonical identification of the field tensored K of G with just K of G. So that's just kind of contracting that tensor, multiplying that tensor out. So right there, that diagram commutes. And that was just me translating left multiplication by E, and then this right multiplication, which is more or less the same, it's just on the other side. So this is ID tensor of E, and this is this canonical identification. This commutes. So this is the co-unital property. Okay, so the associative axiom of the group translated into this co-associativity of the co-multiplication, the unital axiom of the group turned into this co-unital property about the co-unit, this evaluation of the identity. And I'm just left with thinking about the inverse axiom of the group. That should tell me something about this homomorphism I star, the comorphism of inversion. So this has a name too, by the way. This is called the antipode. So let's finally see if we can work out what's going on with that. So let me see if so here's the axiom I'm trying to dualize. Okay, so that's inverse's axiom. So how can we say this? Let me see. I want to take it's a little bit tricky to write this down, so I'm going to take g. I'm gonna use this function delta from g to g cross g, which is this kind of inclusion of the diagonal. So if I apply that to my g, I get g comma g. And then if I apply the function identity cross I to g comma g, that gives me g comma g inverse. And then if I multiply that, that gives me g inverse. I want that to equal e. So how can I get e starting from this element little g? I'm going to need, let me see, I think I'll call it, what did I use pr already? Yeah, I used pr already. That wasn't, let me not call that pr earlier. Let me just call this, let me just write that in there. That was just the projection onto the second factor. Let me use maybe p here. How about that? I mean, this is just the constant function sending everything to e. So you see on the right hand side I want to start with g and I want to apply this constant function taking g to e, and then I want to include e into g. Okay, so that right hand side is a very complicated way of writing e. So there, that's exactly that equation encoded. So we want this to be equal for all g in g. Well, how do you tell if 2 points are equal? They're equal if and only if when you evaluate any function in the coordinate algebra on them, those are equal in the field. And then so I'm maybe making this look much harder than it really is. So what is this? This is so this is all of these morphisms done before f, but that's the same as taking the comorphisms and applying them to f, right? So all of these, I can kind of move them out here and they become the comorphisms. So I get delta star id tensor I star m star. That comorphism applied to f of g, that's just that left-hand side. And here this is, what's this? This is p star evaluation at e, because that's the comorphism of inclusion. So this is for all g and f. But saying this is for all g and f, you can just cross off the g's now because it's for every g, and you want this for every f. Saying that is this for every f, you can just cross off the f's, and there is the diagram that I wanted. So I think if I start at, let me see if I can write this down as a diagram. Okay, so let me try and draw this nicely now. So I'm thinking about the left-hand side, so I'm doing m star. So that goes from k of g to k of g tensor k of g. And then I'm doing identity tensor I star. That goes from k of g tensor k of g to k of g tensor k of g again. And then I'm doing this delta star. Now let's think, what is delta star? So delta star goes from k of g tensor k of g to k of g. It's just the algebra multiplication. So this is just multiplication in that given algebra. So that's my left-hand side. And the right-hand side, so I've got to do evaluation at E, which takes me to K. And then I've got to do P star. What is P star? P star from K to K of G. That's just the unit. The unit map of this associative algebra, right? So it's just the K-linear map, which sends 1 to 1. Okay, so how did I make this look so complicated? I'm not really sure, but there we go. It's not that complicated. So that little diagram has to commute, where this is this canonical inclusion of the unit of the field into the K algebra K of G. So that has to commute, and of course similarly on the other side, so there's another copy of that same diagram with the order reversed. That has to commute. So this is the, so what I already had the co-associativity, the co-unit property, and this is the antipode property. Okay, great. So that was more or less going through that derivation of those silly dual identities is kind of a good exercise sometimes. So here's the definition that this is meant to motivate. An associative unital algebra A is called a bi-algebra if there's an algebra homomorphism called M star, the co-multiplication given, and then algebra homomorphism, I'm just going to use the notation we were just using, so that the diagrams 1, the co-associativity, and 2, the co-unital property, commute. If in addition there's a linear map I star from A to A, so 3 commutes, the bi-algebra is called actually a Hopf algebra. In that case, that linear map I star is actually unique, right? So being a bi-algebra, the M star and the co-multiplication and the co-unit, they're data that need to be given. They're part of the data of a bi-algebra. But this I star, this antipode, if it exists, it's unique. So it's not actually additional data, it's a property of the bi-algebra. If the bi-algebra possesses an antipode, it's called a Hopf algebra. That's a property, not an extra piece of data. And you could show, moreover, that I star is an algebra anti-homomorphism. for free. R I star was an algebra homomorphism, but then our algebra was a commutative algebra. So homomorphism and anti-homomorphism is just the same thing. So that's consistent with what we were doing. This definition that I'm giving you here of bialgebra and Hopf algebra, I didn't assume my algebra was commutative. But if you have an algebraic group, the coordinate algebra is actually a commutative Hopf algebra in this way. I think we should definitely stop right there. I'll give some examples next time, though.